lecture going to be on the video?
Yes. The lectures are going to be, the lectures are already posted, the PowerPoint presentations are being posted. And I'm recording the lectures. I'm recording the lectures as well, and depending on the class attendance, I might post these as well. So that when you, so that you can look at the lecture again when you're doing exams. But it's a double-edged sword to do that, because what then happens is people stop coming to class, right? And think that they can just look at the lecture at home. If that happens, I'm not going to post the lecture, you know, because then I may as well just record the lectures, you know, at my own convenience, and we may, you know, not have any classes. So this is just, you know, to assist you, okay? And I will post them depending on the class attendance. All right. So, okay. Now let's continue. I just want to mention briefly the idea of a catalyst, because we're discussing chemical reactions now, and you're going to look at this in more detail when we're discussing kinetics. But if you're doing a chemical reaction, sometimes you want it to go faster. Some reactions are very slow. Right? Now the notion of speed in a reaction, in German Geschwindigkeit, can be affected by adding a catalyst. Now a catalyst makes a reaction go faster. In other words, it plays a kinetic role. Kinetics is about speed, thermodynamics is about whether or not something actually takes place or not. Now, let's suppose, well, this is again a nice analogy. If you're trying to push a rock over a mountain, obviously it's going to take you much longer to do so if you know, go right to the top of the summit. Let's say you want to get the rock from there to there. This is like a chemical reaction. If you push it over the hill there, that's really, really going to take a lot of work and a lot of time. But if you find a path somewhere in the middle, of course it's going to be easier and the whole process is going to go faster. But you're going to end up in the same position, right? Now that's what a catalyst does energetically. You can think of this as being an energy profile of a reaction. And what it does is it lowers the pathway that the reagents have to go essentially to reach the product. That's what a catalyst does. So if we draw this on a graph, we can imagine the x-axis being reaction coordinates, which we call it. Now we do not call it time, we call it reaction coordinates, and you'll see why in a minute. And this is energy. So let's suppose this is the energy profile of a hypothetical reaction. This is the energy of the reagents, this is the energy of the products. This over here, this hump over here is the activation energy. So the distance between here and the maximum of this point here, this is we call the energy of activation, or EA, activation energy of a reaction. Now if I throw a catalyst in there, what we actually do is we lower the activation energy. Just like we saw with the rocks being pushed along a different energy pathway. So this would then be non-catalyzed, and this would be catalyzed. Now, I should mention that not all reactions can be catalyzed, right? And some reactions happen so quickly that you don't even need to catalyze them. But yeah, catalysis is a branch of chemistry that's very important, and yeah. I just wanted to mention that since we're discussing chemical reactions. Now, here's basically what I've just said, you know, expressed differently. You see we lower the activation energy there if we add a catalyst. Okay, we get different types of catalysts. We get homo and heterogeneous catalysts. Basically, this is something for a later course, but a homogeneous catalyst is one that is in the same solution that the reaction is, or the same phase that the reaction is taking place in. In other words, if everything is in solution, that would be a homogeneous catalyzed reaction. A heterogeneous catalyzed reaction is one where the reagents and the catalysts are in different phases. A classic example of this is probably the most important process in the world, the Haber-Bosch process. What is the Haber-Bosch process? The synthesis of ammonia. N2 plus H2 forms NH3. If it wasn't for this process, the world's population would be much less than it is now. Why? Because ammonia is used in the synthesis of fertilizers, which enables industrial agriculture. Let's balance the equation just for the sake of practice. There we go. Balanced. No? Yes. No. Now it's balanced. 3 times 2 6 is balanced. Okay, that is the Haber-Bosch process. Now it's a very difficult reaction to do, and it requires high pressures and temperatures, but essentially it is a classic example of a heterogeneous catalyzed process. And how it works is essentially you have an iron surface, or some sort of an iron surface, or some modification thereof, and the nitrogen and the hydrogen molecules come and sit on the surface, and at the surface, they basically get stuck onto the surface of this iron surface, and then the reaction takes place, and ammonia is liberated. So you see that's heterogeneous because the nitrogen and hydrogen are in the gas phase, and the iron, which is the catalyst, is a solid. Heterogeneous. Other. Hetero meaning other. Alright, so this is a key process in the world, and without it, again. And incidentally, it basically accounts for a substantial percentage of the world's energy use. That process alone. Alright, so the key thing that I want you to know at this stage is that you have catalyzed reactions. It lowers the energy pathway, speeds up the reaction by lowering the energy of activation, as we see there, and that you have homo and heterogeneous catalyzed processes. We also have catalysis in biochemistry, or in biology. And basically how that works, and you'll learn about this more in biochemistry later on, and also in biology, in core biology, but essentially it's the same thing. You have enzymes, which are really fancy molecules, proteins, which can bind to substrates, and we call this a lock and key mechanism, where you form something like this, which we call an enzyme substrate complex, an ES complex, and then something happens there and you get products. Now, to go from the substrate to these products without this enzyme would be not possible. So this is biological catalysis. Biocatalysis occurs with enzymes, right, which do the same thing as man-made catalysts. So what's happening here is exactly what's happening there. We're lowering the energy of activation. It's playing a kinetic role. Lowering the activation energy, that's kinetics. Okay? Speeding things up. Okay, so these enzymes typically follow something called Michaelis-Menten kinetics, which is something specific to enzymes. I'm not going to go into that now because that's something for a biochemistry lecture, but I just want you to be aware of the fact that bioenzymes are essentially no different from normal man-made catalysts. They do the same thing from an energy perspective. Now I want to move on to something that's of paramount importance. Chemical reaction. Right, let's suppose I have a reaction, right? And I'm forming two products. Here's a generic reaction. A plus B plus whatever forms a series of products. Okay. Now, reactions are reversible. Reactions are reversible. Most reactions, in fact. And that's why I write here reaction coordinates and not time. Because if I were to write time here, if I go from products back to reactants, I'd have to go back in time. It's not possible, right? Well, might be, but I don't think so. I don't think it's very convenient, right? So we call it reaction coordinate because that enables us to consider the reverse reaction taking place. Now, that's exactly what equilibrium is all about. A reaction is at equilibrium. This is the definition. We say a reaction is at equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. What does that mean? It means the following. If I have a reaction, like here I've written A plus B forms G plus H, and the reaction is in equilibrium, it means that the concentrations or the amounts of A, B, G, and H are going to remain unchanged. But there is still a reaction going on in the forward direction and in the reverse direction. It's just that the forward and the reverse reaction have the same rate. So in other words, what's happening at equilibrium is I'm forming G and H from a forward reaction at the same rate that it's being consumed to form A and B again in a reverse reaction. But the concentrations of all are staying the same. That's what it's all about. Now we get different types of equilibrium. And we use a double-headed arrow to show that something is at equilibrium like this. Now, equilibrium does not mean, and students confuse this, that you have A plus B forms C plus D that is exactly the same amount of A, B, C, and D. That's not what it means. It means that the rate of the forward reaction equals the rate of the reverse reaction.
Does it happen at the same time?
So, yes, it happens at the same time.
It's not like if I would have A and B, it converts into
No,
G and H.
it happens at the same time, right? It's synchronous. So you can think of... Alright, so let's just keep things general. A plus B forms C plus D. Let's suppose I have a big chamber. Let's suppose these are gases. And this is A. This is B. C and D. Now those are the proportions, for argument's sake. Now, if I reach equilibrium, the concentrations of all of these things is going to stay unchanged. That does not mean that the reaction has stopped. It just means that the rate of the forward reaction, in other words, the rate of formation of C and D equals the rate of consumption of C and D, or the rate of reformation of A plus B. Then we say it's at equilibrium. Now look at this hypothetical thing here. This reflects concentrations. Concentrations in some sort of a laboratory situation. Now, that looks pretty evenly spread, right? I mean, we've got, quite a lot of A, and B. So the equilibrium there seems to be, in this equilibrium situation, more A and B than C and D. Do you agree with that? Okay, so we would write it then like this. And this is another thing where students get confused and fall down. They think if I write the arrow like that, you see the arrow sits as an equal double-headed arrow. Here the arrow is pointing in the direction of A and B. Why? Because I simply have a higher amount of A and B. The reaction is still at equilibrium. I just happen to have a higher amount of products. That's all that arrow means. It's still at equilibrium. That does not mean that it's not at equilibrium. That is at equilibrium, but the equilibrium is pointing in the direction of the reagents, meaning that there are more of them. Let's consider another situation. Let's suppose I have another, let's say, situation, C, D, A, and B. So tell me, does the equilibrium lie to the product or to the reagent side?
To the reagent.
Right, to the reagent, no, to the product.
Oh, yes.
To the product. So I'd write, in that case, I'd write it like this. Now, of course, one could get very carried away with this. The length of this arrow versus the length of this arrow should reflect, the relative proportions. But, you know, basically if you just make the one arrow bigger than the other, it at least gives some indication as to which side the equilibrium lies on. Okay, now, let's quantify this. Oh, well, let's first look at, let's look at what this actually means. Yes, let's look at some experiments. What actually does this mean? Here I'm taking basically carbon dioxide and hydrogen and I'm making methanol. That's the reaction. Let's look at this first experiment. Forget these two for the moment. What's happening here? Well, this is a plot of moles of reactants and products. Look what's happening here. At the start at T0, so this is now just a plot of measuring the concentrations of carbon dioxide and hydrogen. So this is the reaction I'm actually doing in a gas chamber, let's say. Carbon monoxide, sorry, plus hydrogen forms methanol. Right, I've not balanced the reaction. Let's not worry about that for the moment. We could balance it if we wanted to, but yeah, it's not right now so important. Now, so that's the reaction. Obviously, at T0, I'm going to start off with a certain amount of carbon monoxide and hydrogen, right? Because those are the reagents. At the start of the reaction, there won't be any methanol in the reaction chamber. So that's why it's at the bottom there. Now watch what happens. As the reaction proceeds, this is time. Time is elapsing, and what's happening? What's happening is the reagents, the carbon monoxide and methanol are being consumed, there you can see it, and the methanol is increasing in concentration because it's being formed. Now this goes on for a certain period of time. This goes on for a certain period of time, up until this point here. Then something happens. What happens at this point here? Can someone tell me? Hmm? Sorry?
It's stabilized.
Okay, it's stabilized. What does that mean? Yes, it has reached equilibrium because the amounts of all the reagents are remaining unchanged. You see, that's not increasing, it's flatlining. So is that and that. Does that mean that there's no reaction taking place anymore? No. It just means that the rate of the formation of methanol equals the rate of consumption of methanol and reformation of CO and H2. Does this equilibrium lie towards the products or towards the reactants? No. Towards the reactants. Look at the concentration. The concentration of the products here is 0.1, let's say 1.5. Or let's say, okay, it's not concentration, it's expressed in moles. We've got 0.15 moles, and here we've got 0.8 moles of hydrogen, and yeah, let's say 0.9 moles of carbon monoxide. It's clearly much bigger. So the reaction lies to the reactant side. The reaction lies to the left, but it's at equilibrium. Now, let's quantify this. I now introduce a very, very important constant, called the equilibrium constant. This appears in it's dressed up in various different forms. You have Ka, which is the acid dissociation constant, Kp, which is equilibrium constant expressed in terms of pressures. You have K, just K and all sorts of things. What I want us to concentrate on is K subscript C, capital K subscript C. Now this is a beautiful thing which will tell us just in a quantifiable way whether the reaction is lying to the left or to the right. And that's what this is all about, right? So if the reaction lies way to the right, in other words to the products, we're going to have an extremely high Kc value, because the definition of Kc, as you can see here, is simply taking the balanced reaction equation and looking at concentrations, molarities balanced. Remember we discussed molarities a moment ago. Of each of these raised to the stoichiometric coefficient. That is the formula of Kc. So if the equilibrium lies to the right, to the product side, you can see mathematically Kc is going to be very, very, very high, isn't it? If the reaction, like we just saw, this one here, will this have a big or a small Kc value? Small. Because you can clearly see, let's suppose, okay, this is expressed in moles of reactants. Let's suppose that we do this now in a 1 liter flask, right? Then we can immediately express this in terms of concentrations. You can see the concentration of the product, methanol, is much, much lower than the concentration of the CO and H2, and therefore we're going to have a low Kc value. So this basically enables us, this quantifies the equilibrium, okay? And this is the way that it is expressed. Here's an example. So, all right, here I'm working with gases. That should be yeah, this is the reaction we just looked at. That's the expression for Kc, but that should just be Kc. Just call that Kc. As I said, you get different types of K. I don't want to confuse the matter at this stage. I just want us to consider Kc, which is simply the expression of the equilibrium in terms of molarity, molar concentrations. So here we have an example. We have nitrogen pentoxide, which essentially decomposes into nitrogen dioxide and oxygen. That's the balanced equation. You can see it's very easy to arrive at the expression for Kc. It's simply the concentration of products, here NO2 raised to the stoichiometric coefficient, in this case 4, and the concentration of oxygen, which is of course 1 because there's the stoichiometric constants of 1 there, divided by the concentration of products raised to the stoichiometric coefficient there 2, and you plug the values in and you get Kc. Very simple. Again, most of you should have seen this in high school. All right. This is just something I want to say at this stage. I don't want to take this any further because it's opening Pandora's box. But I say here it's better to use activities instead of concentrations. Now, what that is all about is that is sort of then you can work with something called K, just K, right? Kc is sort of working with molar concentrations which are not normalized. We're just going to work with that now. We're just going to work with Kc, but again, be aware of the fact that there are other expressions of K, the equilibrium constants, and you have the same thing with, you can work with Kp, for example, which is the equilibrium constant in terms of partial pressures and stuff like that. Okay. I don't want to discuss two at this stage because I think it's just going to confuse the issue. Plus, it's really dependent on understanding kinetics, which we're going to do, in fact, in the coming 2 weeks. Okay. Now, I want to introduce another important thing here, and that is the notion of Q. Now, we've just discussed Kc. There is something called Qc as well, which is defined mathematically in exactly the same way. It's just at all points other than equilibrium. In other words, if I have a reaction that's ongoing before it's reached equilibrium, I can estimate the Q value by doing the same thing, plugging in the concentrations and solving for the expression. Now, this basically is very useful because it tells us what direction the reaction is going in. In other words, if Qc equals 0, what does that mean? Well, that's, of course, when we've got no products. Qc would be 0, right? So let's go back to our little graph here. Let's go to T0. Q, defined in exactly the same way as K, just enables us to calculate essentially, what's going on at any point in the reaction, not just at equilibrium. So K is just at equilibrium. Q is any other point that I desire. So at T0, right, notice, what would the value of Q be? What would the value of Q be at T0? 0, yes. Because it's defined simply as products over reactants, essentially, raised to the powers, concentrations and everything, at a certain time t, so that would be at 0. So, when Q equals 0, we're basically at the start of the reaction, okay? And if you calculate a Q value that is less than the Kc value, the reaction is basically lying on the left. If Q equals K, or if QC equals Kc, of course we're at equilibrium, because basically the expression is then identical, and so on. Now Q is important. We're going to revisit Q in the last part of the course when we discuss electrochemistry, and there we're going to deal with something called the Nernst equation, where Q is very important. I just want you to be aware of the fact that Q is something that we have around that enables to predict the direction that the reaction is going in, and ultimately has the same mathematical formulation as K. All right. Essentially, the last thing I want to discuss today is something called the Chatelier's principle. Now, who of you have encountered this in high school?
We haven't, or
Who has done Le Chatelier's principle? Okay, you all look looking around me. Don't be so nervous. Okay, Le Chatelier's principle. What is Le Chatelier's principle all about? All right, let me give you an analogy. If you are, well, let me think of a silly little analogy. I like silly analogies. If you're sitting on a chair and everything is fine and you're happy and the chair is stable, and suddenly somebody comes and pushes you off the chair, what are you going to do? What are they doing? They're disturbing your equilibrium, aren't they? You're sitting on the chair. I'm at equilibrium. I'm happy. Leave me alone. Now somebody pushes me off the chair. What am I going to do? Well, I have two choices. I can either do nothing and fall off the chair, or I can push back. In other words, I can fight against the stress to restore equilibrium. And that's what Le Chatelier's principle is all about. In other words, if I have a system, what it says is if I have a system at equilibrium and I stress that equilibrium in some way, in other words, by heating it, by adding more of one of the reagents, by changing the pressure, whatever, I'm adding a stress to the equilibrium, and the system is going to react in a way as to eliminate or alleviate that stress. That is what Le Chatelier is all about. Let's have a look at this. Here I have an example. I have, this is essentially sulfur dioxide here. Sulfur dioxide reacts with oxygen to form sulfur trioxide. There's the balanced, well, yes, it's balanced equation. Let's suppose that this reaction is at equilibrium. In other words, let's suppose these are gases, I have a gas chamber, and the concentrations of all the gases are staying the same, irrespective of whether the equilibrium is to the left or to the right, it doesn't matter. Now let's suppose I take this system that's very happy with itself, happy at equilibrium, and I inject suddenly SO3 to the gas bulb. What have I done? It's like somebody pushing me off the chair. I've taken a system that's at equilibrium, that's perfectly happy with itself, and I've disturbed that equilibrium because I've added something to it. I've added more SO3. Now the system is going to respond according to Le Chatelier's principle to alleviate that stress. And how does it do that? Well, I've suddenly pushed in, increased the concentration of SO3. The system reacts by increasing the rate of the reverse reaction. And if it does that, what happens? Well, it's trying to alleviate the stress of adding SO3 to the system. So the moment I do that, I destroy the equilibrium, and then there's chaos in the system. The reverse reaction, the rate of the reverse reaction is rapidly increased to alleviate the stress of adding the SO3, and then at some point later on, we will get a new equilibrium with different concentrations. That's Le Chatelier. Let's look at it pictorially. Let's take this very dramatic story of destroying an equilibrium. It is quite dramatic. It's quite violent. Right. Let's suppose, now let's take this equation, so it's SO2 plus O2 forms 2SO3. There it is. All right, so let's draw this situation. This is time, and this is concentrations. So let's say this is SO2, this is the concentration of O2, and this is the concentration of SO3. This is T0. Right, let's suppose now, let's play the game. So I have a bulb, and it's empty, it's evacuated, and I add in SO3, and I add in O2, so that they have the concentration shown there. At T0, I'm not going to have any SO3, right? We've just seen what's going to happen. What's going to happen initially is this. Something like this. All right, at which point do I have equilibrium? Here, is there equilibrium? Here? Here? Yes. Okay, I haven't drawn it very well, but yeah. Essentially, where it flattens out, this is the point, the onset of equilibrium. Because the concentrations are remaining unchanged. Does the equilibrium lie to the left or to the right? To the left, because the reactants are clearly in a much higher concentration than the products. Now, let's play the movie forward. Like I said, I'm now going to inject, suddenly increase rapidly in one go, the concentration of SO3. Let's look at what happens. So let's say at this point here in time, let's call this Tx, I increase the concentration of SO3 with a syringe. Boom. What's going to happen? I'm going to destroy the equilibrium. That's the first thing. The concentration of SO3 is going to shoot up because I've increased the concentration. It's going to go up instantaneously. If I add it in slowly, of course, that's not going to shoot up like that, but let's assume I do it in a single instant. The concentration goes up. Now what's going to happen now is, well, by Le Chatelier's principle, what's going to happen?
They're going to rise into SO2.
Yes. Yes, because by Le Chatelier's principle, I'm going to favor the reverse reaction. So that means the consequence of that is that initially the concentration of this is going to go up, but then it's going to go down again because I'm favoring the reverse reaction. And the concentration of these are going to initially go up and then go, it's going to essentially go up. It's going to look something like this. Because what have I done? I increased the concentration of SO3, boom. Le Chatelier's principle kicks in, and the reverse reaction is favored, meaning that the concentration of SO3 and O2 is going to increase. All right? So you're going to have something like that. But the consequence of the concentration of those two increasing is the fact, and the fact that I'm favoring the reverse reaction, is that the SO3 is going to go down in concentration, isn't it? And that's what the system is trying to do. It's trying to get back to what it had before. Here it was like me sitting on the chair. It was very happy. Didn't want to be disturbed. And then somebody came along and disturbed him. And so what does he do? He tries to get around that disturbance by favoring the reverse reaction. Now you can play the same game by heating a reaction. You know, it depends if it's endo or exothermic, which direction the reaction is going to go in and stuff like that. Essentially, this is the notion of Le Chatelier, and here I have a very nice visual interpretation, sort of a picture of this, just a moment, a video, which I want to show you, and I think this will make it very clear. turn down the sound. All right. Here we have, can everyone see that? All right. Here we have a very nice demonstration. First of all, it will shift to restore equilibrium, or to alleviate, to restore equilibrium and to alleviate the stress. So here we've got dichromate plus water forms chromate plus, so this is the chemical reaction. Let's just stop right there. Right. So that's the equation. Dichromate plus water forms chromate plus 2H pluses. So this is now an equation. If the reaction lies to the left, it's orange because the dichromate ion is orange, and if it lies to the right, it's yellow. All right. So if the reaction has a yellow appearance, it means that it's lying to the right. If it's orange, it means it's lying to the left. Everyone happy? Now let's look at what happens. All right. What would happen if I take a solution of this that's at equilibrium, and I add H plus? What's going to happen by the Chatelier's principle? Will it shift to the left, or what will happen?
It will first shift, well, you increase the product side, and that's why it's going to first turn yellow, but then slowly it's going to turn into orange again because they're going to be. Well,
yeah, it's exactly. Well, it's not going to turn yellow. It's going to. In fact, let's suppose it's orange. Let's suppose the equilibrium is lying to the left, and I add H plus. What's going to happen? It's not going to turn yellow. It's just going to go even more to the left. The concentration of the H plus is going to go up, right? But the equilibrium is going to go even more to the left. Right? What happens if I add OHs? Will it go to the left or to the right? Think about this. Well, what's an OH? An OH is going to react with the H plus here. And what's going to happen? It's going to basically eat up the H pluses and form water, because OH minus reacts with H plus to form H2O. So if I introduce hydroxide, right, it's going to basically take that out of circulation. It's going to be causing a stress. In this case, not adding more H pluses, but doing what? Effectively taking them away. Right? Do you all see that? I see some blank faces. Yes or no?
Yes.
Thank you. So, and that's going to, what's the effect of that going to be? It's going to go to the right. To the right. Because the stress in this case is I'm adding OH minus, it's reacting with H plus, so effectively that is being taken away. That's the stress. The concentration of that is suddenly going to go down, not up but down. So the system reacts in a way to alleviate that stress. How's it going to alleviate it? By increasing the rate of the forward reaction. In other words, we're going to shift the equilibrium to the right. So the Chatelier's principle is all about shifting equilibria by stressing a system. Let's look at what happens. So, there you have it. So there is a system that's at equilibrium, it's yellow. So the equilibrium lies to the right. Now we're adding H pluses, look what happens. It's yellow, it's yellow, it's yellow, and it turns orange. We've shifted the equilibrium to the left by Le Chatelier's principle, and it turns orange. Now he's adding OH minus, it goes back to the right. Look at that. Isn't that incredible? You can manipulate an equilibrium by changing the conditions, essentially. And that's what the Chatelier's principle is all about. Okay, so this is now another, just sort of to end today's lecture off. This is looking at the situation again in a more, let's say, rigorous way. Here we have, again, the situation, our old friend, the sulfur dioxide, well, like I was drawing over there. And you can see basically what happens here in terms of numbers. Here I did it in terms of a graph, right? which is very important. I want you to be able to feel comfortable to plot things. By the way, when I was in high school, we had to be able to do stuff like this in high school in South Africa. Okay. So here's the situation. We have sulfur dioxide plus oxygen forms SO3 there, and let's suppose we now have a system at equilibrium. So here's a 10-liter glass bulb. We have 0.68 moles of SO3, 0.32 moles of SO4, and 0.16 moles of oxygen. Does the equilibrium lie to the left or to the right? That's quite kind of difficult to say, right? Because remember, well, let's write down the expression for K. What is the expression for Kc? Kc is SO3 squared products over reactants, SO2 squared multiplied by O2. So SO3, the concentration of SO3 is 0.68 squared divided by 0.32, 0.16. 0.32 squared multiplied by 0.16. Can someone please calculate this? I want this to be as interactive as possible. Let's calculate it. Now you all have cell phones with calculators, right? Whip them out and let's calculate. So we're calculating the expression for Kc, assuming that this is an equilibrium situation. In other words, if these concentrations are going to remain unchanged. Does someone have a value? A value for Kc.
28.222.
What?
28.222.
28.232.
Sorry, 222.
All right. Does this expression have units? Yes or no? Does it have units? Right. How do we figure that out? Well, different Kc, you've got some Ks, some variations of the equilibrium constant K that is dimensionless, like K. But Kc can have units. It depends on the situation. This is expressed in moles per decimeter cubed. So it's mole per decimeter cubed squared divided by moles per decimeter cubed squared times mole per decimeter cubed. Right. So does it have units? Yes. The units are, in fact, moles to the -1, decimeter to the +3. Is that correct? Yes. So, it's decimeters per mole, which is a bit weird, but yeah. Depending on the formulation of K, it might or might not have units, yeah? Kc might have units. K and other formulations where they sort of normalize are dimensionless or don't have units. This does. Look in your textbook, there's a whole description on this, on different Ks and stuff, but for this course I just want us to concentrate on Kc. So K in terms of molarity. So we get a value of 28.2, so that means, yes indeed, the reaction does lie to the right, a little bit, but it's not like 20,000 or 20 million, you know, it's 28, so it's sort of in the middle, a little bit to the right. Okay, so it's at equilibrium, the concentrations are unchanged, and then I suddenly go and I inject another mole of sulfur trioxide. Now watch what happens. Watch what happens. The concentration after equilibrium has been restored, there's actually the concentrate Kc value. After the equilibrium has been restored, okay? After it's been restored, look at the new concentrations. So what we're going to have is we're going to have a time where there's some chaos. The initial equilibrium is destroyed. We've messed things up. There's a state of chaos in the system. And then a new equilibrium is restored. A new equilibrium. A new equilibrium. But, by Le Chatelier's principle, the concentrations are going to be different. So because of Le Chatelier's principle, we favor K minus 1, in other words, the reverse reaction. So the concentrations of SO2 and O2 are going to increase, and they do. The concentration of SO3, of course, is going to be higher because I've added an extra mole of SO3. But notice, I start off with 0.68 moles, I add 1 mole, and I end up with 1.46 moles. So it's lower than it would have been if I just added the two together because the reverse reaction is favored, exactly as I drew it here. So it increases and then decreases. So this is essentially what I've represented here. And this is very important, right? Being able to really understand the Chatelier's principle, really understand the spirit of it. It is a way to restore equilibria and to eliminate or try to deal with stresses on a system. It's very, very dramatic. Okay. Are there any questions? Today's lecture, I think, was a little bit slower than last week, right? I hope so. Because I think last week, some of you looked a bit shocked. So, that's why I've decided to say things a little bit slower today, so you can catch your breath. Are there any questions on anything we've discussed today, please? We've got 15 minutes now. I want us to have sort of an open discussion. Questions? Yes?
You looked at the value of Kc and deduced which way the reaction was shifting after you added the SO3. I didn't get that.
So, sorry. Well, what I was doing was I was just evaluating yeah, I understand. I was just evaluating the value of Kc from these concentrations over here, right? From these concentrations over here. And, well, I assumed that we had a concentration of, okay, not 10 liters, but 1 liter. That's an important point. The way that we've calculated Kc here, I assume not a 10 liter bulb, but a 1 liter bulb. All right? If it was 10 liters, then the value would be 2.8 times 10 to the power of 2. I got just 28, so 2.8 times 10 to the power of 1. Right, so if I'd calculated the concentrations in a 10 liter bulb, how would I do that? 0.68 divided by 10 would be the molar concentration of SO3. 0.32 divided by 10 would be the molar concentration of SO2. So that's basically converting to molar concentrations. Right, so in the way that I calculated it was assuming, which was wrong, because it's a 10 liter, not a 1 liter bulb. But you know, you know how to, please tell me you all know how to calculate Kc. Let's do one example.
But if Kc is high, then the reaction is going
Forward. Kc is high.
Yeah, my question is actually, so you looked at the value of Kc and then said the reaction can go the other way.
No, I understand. No, I was trying to establish if the equilibrium lies to the right or to the left, right? So if Kc is greater than 1, in principle, it's lying to the right. If Kc is some positive value, it's always going to be positive. But if Kc is some value greater than 1, it basically means it's, strictly mathematically speaking, that there are more products than reactants, per definition. Because the definition is products over reactants. So, you know, mathematically, if it's greater than 1, the equilibrium lies on the side of the product. If it's less than 1, like something, you know, like, I don't know, not less than, yeah, if it's, let's say, well, it can't be negative, obviously, but let's say if it's 0.5 or 0.000005, right? That is something like a number over a big number, mathematically, meaning that there's more products, more reactants than products, so the equilibrium would lie to the left. You must be able to figure this out. And it's actually just mathematics, right? Because we're looking at products over reactants. So if there's a high value, if K is a big number, it means I've got a high concentration of products. If K is a small number, 1 times 10 to the minus 10, then it means I've got a lot of reactants and not a lot of products. Okay, does that answer the question? All right, sorry, in a very long-winded way. Next question. I want more interaction in this class, yes.
Then how did you convert, after adding 1 mole of SO3, did you have those values on the right side?
Oh, these values here?
Yeah.
Oh, these values, you wouldn't be able to calculate them. This is something that you'd find experimentally, right, in a laboratory. But it demonstrates Le Chatelier's principle, right, because it's essentially what I've drawn here. This is sort of what you would qualitatively see, right, the moment you add a stress to the system, right? In this case, increasing the concentration.
Okay.
You can also decrease the concentration like we saw in that video. You know, so you run in the direction that's going to alleviate the stress. Incidentally,
So
yes?
we're just most focusing on the concept more than exercises in here.
Well, I want you to understand the concept and also, depending on the situation, be able to qualitatively actually predict what's going to happen, yes. One further thing about Le Chatelier that we haven't discussed, just I want to spend 1 or 2 minutes on this. We've looked at stresses concerning changes in concentration. But what about, for example, heating a reaction? Now that would depend on whether the reaction is endo or exothermic. What means endo or exothermic? It means if I, for example, have a transformation, A goes to form B. Let's keep it simple. A goes to form B, delta H is positive. What does that mean? So the forward reaction is going to be endothermic, meaning it's going to look something like this. Now I really hope you all did this in high school. That is delta H. This is H, reaction coordinates, endothermic. Now, what does that actually mean? It means that the forward reaction, in order for its, well, the forward reaction requires or it pulls in energy from its heat energy from its surroundings. It's endothermic. What's the opposite? Exothermic. A reaction that gives off heat. Let's look at another scenario, another hypothetical scenario. C goes to form D, and in this case delta H is negative. It looked like this. That is delta H. Exothermic. Now, let's suppose the top reaction, A goes to form B, which is endothermic. Let's suppose it's at equilibrium. Let's suppose it's at all nicely and happy at equilibrium, meaning A is going into B and B is going into A. Now here's the question. What would happen if I heat it up? Would the reaction go? Where would the reaction go? Would it go forward or back? I think very carefully.
Would A and B?
Yeah, this one here. I take it it's at equilibrium, I heat it up. Would the reaction go forward? In other words, would the concentration of B increase? Or would it go back? Would the reaction, the rate of the reverse reaction increase? And effectively, would the concentration of A increase? What would happen?
B would increase.
What?
B would increase.
Yes, B would increase. Why?
Well, it's an endothermic reaction, so it needs energy from the surroundings. So if you add energy, then the product rate is going to higher. It's going to be higher.
Well, yes, but you've got to be very careful, right? Because the reason is a little bit more subtle. It's a little bit more subtle, right? Yes, you're right. But the reason is that I'm adding a stress to the system. I'm putting heat in, and the way that the system deals with that stress is by going in the direction that it's going to get rid of that heat stress, which is the direction of the forward reaction, which happens to be endothermic. And so if I promote the forward reaction, then I'm going to, at least get rid of some of that heat. That's the reason. Okay? Yeah, expressed in a more formal way. So yes, what would happen if I were to cool? Now let's think about this. If I take this transformation here and I cool it down, I put it in an ice bath, what would happen? Would the left or the right be favored? You see, it's kind of difficult. The stress is I'm cooling it down. So, by Le Chatelier's principle, the stress is I'm cooling it down, so it's going to go in the other direction. Because if it goes in this direction, the forward reaction is already endothermic. That means already taking in heat. Now I'm stressing it further by even cooling it down. It gets away from that stress by going in the other direction. Let's play the same game with this transformation here, C to D. This is some hypothetical reaction. It could be A plus B, it could be whatever. It's just a transformation. The forward reaction is exothermic. What would happen if I heat it up? Would the forward reaction be favored or the reverse, by Le Chatelier's principle? Yes, because the forward reaction is exothermic. So it's already producing heat. Now if I heat it, that's a stress. It's going to go in the other direction. What if I cool it down? All right, so you guys sort of understand this, right? So there's the stress of heat, and then you've got to look at whether or not the reaction is endo or exothermic. There's the stress of concentration and the combination of these things. You could heat something and at the same time, but the point is you can manipulate the position of the equilibrium by simply changing the conditions. Any other questions?
Why do you do that? For what reason?
Well, sometimes, it's fun.
Okay.
No. I mean, the real reason is, of course, it's fun. But the reason is that sometimes if you have some sort of a chemical process where you're making some product, it's sometimes useful to be able to manipulate the position of the equilibrium. In other words, change the concentrations of gases and stuff like that to change how much product you're making. So it's a very important thing in industry and chemical engineering, which we're looking at, of course, on a very simplified level, but it is very important. And of course, fun. And you can change the color by cooling something down and heating it up, and so it's kind of very interesting, I think. Any other questions?
Just a small question.
Yes?
How the decimeter +3? How do you end up with plus?
Because if we go through the math, the units of this is moles per decimeter cubed, right? But the concentration here is squared. So it's in fact anyway, at the top we have moles per decimeter cubed for that one. The SO2 is also moles per decimeter cubed squared, so those two cancel. And we're left with at the bottom is moles per decimeter cubed. So it's in fact, it's 1 over moles per decimeter cubed, so that's moles to the -1 decimeters to the +3. It's exponents, laws of exponents. I mean, it's kind of a silly unit, but it's a unit nevertheless. So Kc has units, K does not, and other variations of K expressed in terms of normalized concentrations and activities and stuff like that. You will see in the textbook a very nice table where they have all the different variations of K. Again, I'm just interested in this course in Kc. This is not a thermodynamics course, this is a course in general chemistry, and Kc I think suffices for all purposes.
What is activity that you just mentioned?
Yeah, activity has a definition where you divide, I think there's a certain formula, but it's essentially concentration divided by it's written as A. So you can express it, it's got a certain definition. I can't actually remember the formula, but you can express K in terms of activity as well. What we're going to encounter later on in the course is Ka, which is the acid dissociation constant, which is effectively Kc just in terms of acids. That's the only other K that we're going to discuss. Fabrice is going to be doing the thermodynamics lecture. He may introduce some other forms of K, but I'll talk to him about that. I want to keep it simple. Any other questions? Yes.
And is there a worksheet this week?
Sorry?
Is there a worksheet?
Yes, I've uploaded it this morning onto Inil. It's uploaded. So we will grade these and get these back to you next week, or probably by Thursday. I want you to please keep these. You must keep them. All right? We're going to give them back to you, but at the end of the course, I require them all back, because at this university, everything needs to be retained. So please return everything. But then you can see where you went down. How did you find the tutorial? Was it doable?
Yeah.
Good. And I encourage you to work together and help each other. I don't have a problem with that. Today's tutorial, my tutorial group will be run by Fabrice, because he's doing a lecture when his tutorial group is going, so we're swapping today. Today we're going to, in the tutorial group, just have the post discussion, and we're going to discuss this tutorial. I want to make sure that everyone understands this stuff. What I also want to discuss in today's tutorial is I want to look a little bit at dipole moments, and I want us to look at hybridization. Okay? But we're going to not have any pre-discussion today.
So you don't have to have your booklet.
No, but we're going to have the post-discussion of the task 2. Okay, so that's the end of the lecture. See you later. Have a nice week. Ciao.
Yeah.